Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, no problems. Today we're going to talk about Kepler's third law. This is super cool. Like planets revolving around the sun, moons revolving around planets. Actually, our solar system, do you know our solar system revolves around a central black hole in the Milky Way? The principles of gravity and Kepler's third law tell us how this works. We've learned about the first two of Kepler's laws. Remember, the first one is that remember, the first one is that things orbit in an elliptical orbit, and number two, the law of equal areas. And Kepler's third law has to do with how long the orbital period is. So let's get at it. So what Kepler said in his third law, that if we have, an elliptical orbit, remember that the sun, if you will, or the object with the gravitational body is one of the foci of the ellipse, and he said that the size of the planet's orbit, is simply related to the period of its orbit. All right, period, all that stuff. It actually comes down to a relatively simple equation. T cubed equals a squared, where t is the period of the orbit. Now, what's the period of an orbit? Our Earth revolves around the sun for 1 year. It takes 1 year to make one navigation around the sun. So the period is how long for one rotation, right? One rotation is the period, and A is a weird thing. This is called the astronomical units. In astronomical units, a very simple idea. The idea it's the distance. It's really the radius of the Earth to the sun. So in Earth, this is super easy. The period of orbit is 1 year, and the distance is one astronomical unit. So 1 cubed equals 1 squared. So that's super easy because it's all cubed and squared. But the game changes when we talk about like Mars, where of course the period of orbit's more, and the astronomical unit is more. It's further away from the sun than the Earth is. And so this leads us to some interesting problems that we can use with this like super cool equation. And as a note, this is the simplified equation. The actual fancy equation, if you will, Kepler's real third law, is that the T is equal to 2 pi over g times the mass of the orbiting object, let's say the sun in some cases, assuming we're working with the sun, times r to the 3/2 power. That's a crazy equation, isn't it? But it can be simplified into this simple equation if we work not in big fancy units like g's and m's, but in t cubes and a squared. We can actually, let's take this equation and make it even more practical. What we often will do is we'll compare the orbits and the periods of two different objects that are revolving around the same object. So sometimes you'll say t1 over t2, all right, squared is equal to r1 over r2 cubed. Did I get these wrong? Guess what, guys? It's t squared and a cubed. That's the equation. My bad. I knew something was wrong. All right, so this will really be the equation that we're going to primarily use. All right? One other thing we should talk about before we do some examples, there's a concept called orbital speed. So we've got a elliptical orbit. It's moving off, if you will. Remember we talked about this. It's tangent to the ellipse, and this is the speed, the v. And the orbital speed is equal to the square root of g times the mass of the orbiting thing. Let's say the Earth, the sun, or whatever, divided by r. Right, it's going to be in meters per second. So we can figure out what the orbital speed of something is. So let's do some examples. In fact, our first example has to do with this idea of orbital speed. So you can see the example here. And two satellites orbit the Earth. Satellite 1 at a greater altitude than the other. Which one has a greater orbital speed? Now we can use this equation. It's quite simple. If you have one where r, if r is on the bottom of this equation, and one is r, it's bigger. Let's think about this. If r is bigger, what happens to the orbital speed? it goes smaller. And this makes sense, right? So if I've got, you know, the planet here, and we've got one orbit, and then we get another one inside, this one's going to be moving much faster because, why is it moving much faster? It's moving much faster because it's closer to the Earth, and the r is smaller. So you can think about it mathematically, but we also realize that the force of gravity is greater when it's closer to the planetary object, so it's going to be moving faster. So the actual orbital speed of things closer to the Earth, satellites and such, is much faster than ones that are way the heck up, much further up. So orbital speed. But part B, let's look at part B. It says, what is the actual orbital speed of something that's 2 Earth units away? All right. Now, I don't have the numbers all right here, but we can put them in there. We would just plug it in, right? Equals G. We know we're 6.67 times 10 to the minus 11th. We've seen that number a time or two, right? Times the mass of the Earth, 5.97 times 10^24 kilograms, divided by... Now, if it's 2 Earth orbits, we will take 2 times the radius of the Earth. And the radius of the Earth is 6.37 times 10 to the 6th meters. Of course, that's all under the square root thing. Now, I'm not going to get the calculator out, but you got to get careful on this. It's a mess, right, mathematically. And you come up with 5,590 meters per second, which is still crazy, right? Like 5,500 meters a second? It's like 550 football fields a second? Guy's buggering along pretty fast, isn't it? So that's the orbital speed of an object that's traveling at 2 Earth orbits away from the center of the Earth. Now let's actually use Kepler's third law on this next example here, right? You've got the Earth orbits the Sun at 1 astronomical unit, right? Okay. Suppose a new asteroid's discovered, and it's 9 astronomical units. So again, we've got our Earth, and it's orbiting at 1, but way the heck out here, we got some asteroid. This is 1 AU, and this is at 9 AUs. So how long does it take to orbit the Sun? All right, we're going to use our cool equation, right? We're going to say t squared equals a cubed. Now remember that technically the equation really is t1 over t2 squared equals r1 over r2 cubed, where r is the distance from the Sun, or a in astronomical units, and we're in astronomical units, that we can plug this in. But the beauty of this, if you will, is if we're going to compare this, the 2's could be the Earth, and this is 1 and 1, and then 1 cubed and 1 squared is the same number. So we can actually just simplify it with this equation right here. So we know that the astronomical unit, it's 9 astronomical units away, so we can say t squared is equal to 9 cubed, and then 9 cubed is this like 700 something, right? 9 cubed is 729, and that's equal to t squared. Now remember, t is the period in astronomical units, like it'll be 1 year, right? And so we take the square root of both sides, right? And the square root of 729 is 27. And so if we're assuming that the period of the Earth is 1 year, this is 27 years. So something that's 9 astronomical units away from the Sun is going to take 27 years to make its circumnavigation. And our last example, what if you don't have, you know, the nice pretty ones from the Earth and all that cool stuff? So we've got Titan. Titan is one of the moons of Saturn with a radius. So we know something about the first planet, or the first moon, and that is Titan. So we know that the period of Titan, t sub t, is 15.95 days. Now we've got days now as our unit. And we know the orbital radius of this is 1.22. So we can say this is it's R1 is equal to 1.22 times 10 to the 9th meters. And T sub h of the Hyperion, right? That's the one we're trying to solve for. And the R of Hyperion, and we do know that number, that's 1.48 times 10 to the 9th. So now we're going to plug it into our equation. If you recall, the equation is, let's say TT, if you will, right, over TH would be equal to RT over RH. And this side, of course, is squared, and this side is cubed. Now we're going to plug these numbers in here and solve them. That's a little trickier, right? So I'm going to say 15.95 over TH squared equals 1.22 times 10 to the 9th over 1.48 times 10 to the 9th, and that's all, shall we say, cubed. So we can take this, now by the way the 10 to the 9th will cancel, so it's 1.22 over 1.48, and that becomes 0.824 cubed, which comes out to be 0.560, and that's equal to 15.95 squared, I'm doing this real fast I know, is 254 over TH squared. So now we're going to say T sub H squared is equal times 0.56, I'm cross multiplying, equals 254. Divide both sides by 0.56. 5/6's cancel, and then you take the square root of 254 over 0.56. And you come up with 21.3 days. So it makes sense, right? This one was 15 days, and this is 21 days. And look what happened to the radius. This went from 1.22 to the 9th to 1.48. So it's further away, so it's going to have a larger period, so 21.3 days. Houston, the math might look crazy, but it's just like squares and cubes, not crazy hard. It's just like cross multiplication, but with squares and cubes. Kepler's third law, really, it tells us so much, and like we've talked about, gravity has been so successful. We've learned so much about like the universe from the applications of how gravity works, which in Kepler's law is an extension of the law of gravity from Newton. We've got no problems. We'll see you in class.